How's it going? We're Team 7, and today we will be comparing the variance in aluminum and steel. I'm Matthew Compton.
I'm Callie Greenbaum.
And I'm Kaylin Myers.
For this project, we use the Universal Testing Machine and Video Extensometer to measure the elongation and ultimate tensile strength of 5052 aluminum and 1008 mild steel. Steel and aluminum are popular metals for real-world applications. Aluminum is used in aircraft fuel and oil lines, building facades, roofing, marine parts, electronics, and more. Steel is used for automotive body panels, structural elements, and kitchen appliances. In order to apply these metals to the listed applications, material engineers conduct tensile tests to gauge the strength and ductility of the materials.
Okay, so our research questions include how does strain rate affect ultimate tensile strength and elongation, and how do these effects vary with different metals? So our hypothesis is that lowering the strain rate is going to increase the elongation and decrease the ultimate tensile strength. However, we believe that steel will elongate less and yield a higher tensile strength due to its real-world applications. We are going to be measuring ultimate tensile strength and elongation and how these are affected by metal type and strain rates.
Just a quick summary of our equations. The one on the top left is our percent elongation, which is the change in length over the original length. The one on the bottom right is our ultimate tensile strength. This is the maximum force applied divided by the cross-sectional area of the gauge length. The graph you see is just a summary of what we'll see later on. The top of the graph is the ultimate tensile strength, and the X region is the elongation. This is just the ASTM standard dog bone that we'll be testing. This is just the general shape used to test ultimate tensile strength and other material properties.
So here's a schematic of the UTM, and this is a quick list of the procedures that I'm going to go over in depth right now.
All right, this is our video extensometer. It is $16,000, and as you can see, it's given to us by the ITLO. To power this device on, you first have to clip it into the mount. Once it is secure, we can lock it into place with this lever, preventing it from slipping out. And we can also lock the arm to keep it from swinging. After that, you have to secure the two wires to the device. And then we want to orient both our universal tensile machine jaw grips in a 90-degree orientation. Pull it up a little bit. I'm getting frustrated. Our specimens are ASTM standard dog bones. In order to calibrate the extensometer, we first place our calibration piece onto the dog bone and place it in our tensile grips. We want to make sure that the grips pierce the metal right before the fillets on both ends. This will just allow the main force to be in the gauge of the dog bone. In order to use the tensile machine, we first must turn on the machine. After that, we use the TW Elite software. It's how it converts the data acquisition system into usable data, pretty much going from analog to digital. Once in the test section, we'll go to TWEM. We'll go to the bottom, which is MTSEN tension, which is just a simplified tensile test. Once the software is uploaded, we can adjust our test rate. For this first test, we'll be going at 0.1 millimeter per minute. We will be using the preset software of data acquisition rate of 10 hertz.
Open the MTS Video Extensometer software. So we're going to be measuring the strain of the extensometer. Okay, so in the MTS Video Extensometer software, we're going to choose a 100 hertz sampling speed. And now we need to line up our calibration device with this video. Look at that. Yeah, right on the line. Our calibration device is within frame. We need to set up each point to line up with the white dots. I don't really know how to do that. So now we do a validation check. As long as this blue cursor is within this green area, we're fine. And we can see that these red marks line up with our white dots, so we're gonna click finish. And then now we are able to track these 2 white points. So now that our video extensometer software is calibrated, we're going to go over to the MTS software and we're going to 0 the crosshead, and we're also going to 0 the load somehow.
And we 0 the load so that any of the applied forces from the grips are zeroed, and we have consistent readings across all sample sizes. As you can see, it's just bouncing, but it's relatively bouncing around 0. That just accounts for like the grip strength and a little bit of the uncertainty in the machine.
Okay, so now that both of our softwares are calibrated, we're going to use this dog bone marked with 2 dots, and this is what our video extensometer is going to track, while the UTM pulls it apart. So we're going to go ahead and take this piece out and put this piece in. And this one is ready to go. So in regards to the MTS software, we need to track these 2 black dots. So we're going to put these boxes over those 2 black dots and go to start testing. And now we're ready to go for both. And we need to click both at the same time. So I'm going to do that right now. Black dots are going further apart on the software. And then you can also see them moving apart on the UTM. Oh, that's true. Now you can see on the MTS software that the dog bone specimen broke. Cool. And then I'm just gonna do another one.
In terms of our specifications, our $60,000 laser extensometer boasts a measurement accuracy of 0.5%. For our universal testing machine, our force accuracy is plus or minus 0.5 newtons, so both are very accurate. The table you see is just a summary of our 3 tests at 3 different strain rates for steel and aluminum. In terms of our elongation, our initial hypothesis was correct that decreasing strain rate increased elongation. However, our material hypothesis was wrong, as steel elongated more than aluminum, as you can see in the table. However, this might not be entirely true, as you can see by our percent off theory. Steel was very accurate with a 10% elongation for steel, but aluminum was anywhere from 70 to 50% off the 12% elongation for it. This may be due to slipping of the grips or material variability where there's stress concentrations in the crystalline structure, but it's most likely due to the strain sensitivity of aluminum, as it requires a slower strain rate in order to show true elongation, as we talk to the ITL engineer. The following table is just a summary of our ultimate tensile strength. Our initial hypothesis was incorrect that decreasing strain rate did not decrease ultimate tensile strength. But however, on the other hand, our material hypothesis was correct, still did have a higher ultimate tensile strength than aluminum. And as we compare to theory, we can see that both these tests are relatively aligned, with steel roughly 8% off and aluminum roughly 3% off. These are just a visualization of the strain rates. As you can see, still greatly elongated farther than aluminum and had a higher ultimate tensile strength. But as we increase in strain rate, the elongation decreased, but the ultimate tensile strength relatively stayed the same. One quick note is like the squiggliness of the aluminum line. Talking to the ITL engineer, this could be due to slipping of the grips, aliasing in the machine, and or likely due to the too high of strain rate that our aluminum samples were undergoing. These are just quick summaries that we had for ultimate tensile strength, the elongation, ultimate tensile strength, and the summary of our graphs. We also did an ANOVA test to see our factors, how they affected elongation, ultimate tensile strength. For this table, we saw that Our material factor and strain rate were not statistically significant in affecting elongation, but the interaction effect between the two did have a substantial impact on the elongation of our aluminum and steel pieces. In terms of ultimate tensile strength, we found through our NOVA test that the material and strain length were both statistically significant as individual factors in affecting ultimate tensile strength. And additionally, there was an interaction effect between the material type and strain rate, where their combined effects did impact the ultimate tensile strength. In terms of our conclusion, our recommendations for the future are to experiment with more metal types, experiment with slower strain rates, as you saw with the aliasing slightly with the aluminum and how it's off the %30 for ultimate or elongation. And we additionally would like to take a large amount of samples to create a normal distribution and see the upper and lower portions of our quartile. So in conclusion, like we saw, still showed greater elongation aluminum, which disagreed with our hypothesis. Still showed higher ultimate tensile strength than aluminum, which agreed with our hypothesis. Just a kind of summary of our analysis is that higher strain rates likely limited aluminum's elongation, and our ANOVA indicated that material type and strain rate significantly affected ultimate tensile strength. Our elongation was significantly influenced only by the interaction of the material types and strain rates. This is the end of our presentation. We hope you enjoyed. Thank you.